All right, we're going to go through some biochem stuff. Um, these PowerPoints are not from your textbook, so the chapter numbers are not correct. But anyway, we're going to cover some more biochem stuff, and then we'll go through chapter 22 tomorrow. All right, so we're going to start with our lipids. All right, so your lipids, these are your biomolecules that contain fatty acids. So a fatty acid is a long-chained carboxylic acid, and so it will have a carboxylic acid, but it will have lots of carbons. So, all right, so you're going to have between 12 and 18 carbons total, and it has to be an even number. So it's going to be 12, 14, 16, 18. Those are the common fatty acids. All right, and so, or your molecule can contain a steroid nucleus, and that is a six-membered ring fused to a six-membered ring, and then another six-membered ring, and then a five-membered ring. So anyway, it's three six-membered rings and a five-membered ring. Your lipids are organic. They are nonpolar. They will only dissolve in organic nonpolar solvents. They will not dissolve in water. All right, and the word lipose comes from the word fat. That's Greek for the word fat. All right, so we're going to talk about waxes, fats, oils, glycerophospholipids, prostaglandins, and steroids. All right, so this is all of the lipids. All right, so that's at the top of the list here. We have our fatty acids. And again, that's a lot of carbons. So you're talking 12 total to 18 total carbons, even number for your fatty acids. The ones that do not contain fatty acids are the ones that go down here. Then they have your steroid nucleus, which is a six-membered ring, a six-membered ring, a six-membered ring, and a five-membered ring for your steroid. All right, so your fatty acids, you have your prostaglandins, and then down here you're going to have your waxes. Now, your wax is a fatty acid, which is a carboxylic acid with a lot of carbons. All right, and then a long chain alcohol. So now you got an alcohol that now we're going to lasso water and we're going to form an ester. So this is going to be an ester, and long chain of carbons. So you have an ester where you have a long chain of carbons on the left and the right side of your ester. Your triacylglycerols, so you got your glycerol, which is a CH2OH to a CHOH and a CH2OH. That's your glycerol. That has three alcohols. And so you have three fatty acids. You're going to lasso water three times. And so this is a triester. It's an ester group here, it's an ester group here, it's an ester group here. All right, your glycerophospholipids. All right, again, you got your glycerol, and so you're going to have your ester, but here we're going to add a phosphate, which is a PO4 group. So you got your OH, you're going to lasso your water. All right, and so you're going to have your PO4 here, and then you're going to have that connected to an amino alcohol. All right, so your phospholipids, you have your polar head. Here's your polar head. And then you have your nonpolar tails. And so you see that picture in biology a lot. That is your polar head and your nonpolar tails. That's going to be your phospholipid bilayer. And that is your glycerophospholipids. All right, so your fatty acids, long chain carboxylic acid, typically 12 to 18 carbon atoms. It's going to be an even number of carbon atoms. All right, Everything that we're talking about in the lipid chapter is insoluble in water. They are going to be soluble in organic solids. We're going to talk about saturated fatty acids, which means no carbon-carbon double bonds, and unsaturated fatty acids, which means you have a carbon-carbon double bond. Now, we want to have a cis carbon-carbon double bond, because if we have a trans carbon-carbon double bond, now we would have a trans fat. And trans fats are very unhealthy, and so you want to have an unsaturated fatty acid, but those unsaturations have to be in a cis form to make them a healthier choice. All right, so saturated, that just means you got all single bonds. Unsaturated means you're going to have a double bond. And the way they're showing this double bond, they're showing it as a trans double bond, which would be a bad geometric arrangement for your double bond. You want it to be cis, not trans. All right, so if you have your fatty acids, you note that they will pack perfectly, nice and symmetrical. They're going to pack very tight. These are going to be solids. All right, so they pack close in a crystal lattice. And so they have high melting points, which means they are solids at room temperature. You have to heat them up to make them into a liquid form. And so again, solids at room temperatures, these are going to make your fats. Solid fats at room temperature. When you are unsaturated, now they do not pack very well. And they have low melting points, which means they are liquids at room temperature, and we call these oils. So when we have our fats, which are going to be solid, and our oils, which are going to be liquids, all right, the only difference in their structure is your fats are going to be saturated. Your oils are going to have cis carbon-carbon double bonds, at least one cis carbon-carbon double bond. All right, so here's some fatty acids. So here are your saturated ones, which means they have no double bonds. All right, and then you have your melting points. All right, so all of these melting points are higher than the 20 to 25 degree temperature, room temperature. So these are all solids at room temperature. You heat them up and then they will liquefy. All right, and then when we look at our unsaturated, all right, and so now we have our melting points here. All right, so we see that all of these, 25 degrees Celsius is higher than the melting point. So these are all liquids at room temperature, even a cold room temperature of 20 degrees Celsius. That would be a liquid. Note that we have a 16 carbon and an 18 carbon. All right, so as you increase the carbon, so these are all saturated, as you increase the number of carbons, you increase the molar mass, you increase the melting point. All right, and so when you had 16 to 18, you increased the melting point, but it didn't increase it enough to make it a solid at room temperature. But here we have another 18 carbon, except now we have two double bonds. And so again, the double bonds really lower your melting point. All right, so they make that kink in your structure. They can't pack very well into a crystal lattice, and they have lower melting points. All right, and so if you have a high melting point, you're going to be saturated. If you have a low melting point, you're going to have lots of unsaturations. And if you're between them, you're going to have one double bond. So if you are saturated, you're going to have the highest melting point. If you have a lot of unsaturations, you're going to be the lowest melting point. All right, waxes, fats, and oils. So waxes, they are esters. Again, a long chain of carbons with a carboxylic acid. A long chain of carbons with an alcohol. You lasso water, that's how you form your ester. And so here is your ester group. On this side, we have this carbon plus 15 more. And then on this side, we have 30 carbons. Okay, so you got lots of carbons on both sides of your ester. And that is going to be a wax. You got your beeswax here. So all of these have a lot of carbons on both sides of your C of your ester group. This one has 21 plus 25 more and 30 on this side. This one has 20 on this side and 20 on that side. So you have lots of carbons on both sides. And that is going to be a wax. All right, so fats and oils. Again, fats are going to be made with saturated fatty acids. Oils are going to be made with unsaturated fatty acids. All right, they are both triacylglycerols. We're going to have 3 ester groups. All right, and so when we look at our first one, you see that these are saturated because there are no carbon-carbon double bonds. All of these are single bonds, so that's saturated. And so when you have saturated fatty acids, now you're going to form a fat. And a fat just means it's going to be a solid at room temperature. All right, if you're an oil, you're going to look very similar, except you're going to have double bonds here, cis double bonds. You're going to be a liquid at room temperature, and you're going to be an oil. All right. So again, all single bonds, all single bonds, all single bonds. So you have a fat, which means you have a solid at room temperature. All right, because these are saturated. So that's how you will tell the difference between a fat and an oil. Everything's going to be the same, but if you have double bonds, now you're going to be a liquid. Now you are an oil. If you have no double bonds, then you're going to be a solid and you're going to be a fat. All right, so here you see we have a carbon-carbon double bond. All right, and so this is an oil. This is going to be a liquid at room temperature. All right, so this is a one unsaturated, mono-unsaturated fat. And when you have an unsaturation, your melting point is going to be low, which means you're going to be a liquid. And that is then called an oil. All right, so that is the difference. So you need to know the difference between a fat and an oil. One, well, the fat is a solid at room temperature. Liquid is an oil. Oil is a liquid at room temperature. All right, so prevalent in meats, whole milk, butter, cheese, and now your oils are plants. So you got your olive oil, safflower oil, you got your vegetable oils. All right, so the difference is fat is solid room temperature, oil is liquid at room temperature. Fat is made from saturated fatty acids, and oil is made from unsaturated fatty acids. All right, so your oils, you're going to have unsaturated fatty acids. You're going to have not just unsaturated, not just carbon-carbon double bonds, but cis carbon-carbon double bonds. You do not want the trans carbon-carbon double bonds. All right, so that makes kinks. It doesn't pack very well. That's why it has a low melting point and it is a liquid at room temperature. All right, so liquids at room temperature, that's your oils. All right, so here you have a cis double bond, another cis double bond, another cis double bond. All right, and so you have an oil. So you can tell it's an oil just by the cis carbon-carbon double bonds in your long chain of carbons. All right, and so the cis double bonds, they make it very difficult to pack, which means you're going to have a low melting point, which means you're going to be a liquid at room temperature. All right, and so here are percent saturated and unsaturated fatty acids in your fats and your oils. Um, Normally, polyunsaturated, you would think, is the most healthy, but it depends on who you're talking to. But olive oil is supposed to be the healthy oil, and you see that in olive oil, you have mostly mono unsaturated fats versus your polyunsaturated fats would be your sunflower and your safflower and your soybeans. So they have very high polyunsaturated uh, fatty acids. But sometimes if you have polyunsaturated, some of them could be trans fats, which could lower their health. And so your olive oil is pretty healthy. You see your coconut oil, which people will cook a lot with, and they'll say it's healthy, but it is pretty much all saturated, so it's just as healthy as cooking with butter, I guess. Although butter looks more healthy by percent saturated, unsaturated to me. But that is for a research topic. 4. All right, your chemical properties for your triacylglycerols. All right, so this is where you have Crisco, which is interesting because it's called vegetable shortening. All right. Well, this was made in the lab. Normally I support my lab making things, but not in this case. All right. So if you want to make margarine, it's vegetables made from vegetables. All right. So it was a liquid. It had healthy uh, carbon-carbon double bonds that were cis, and then we did a reaction and made them saturated. All right, and so we did a hydrogenation, which means we added hydrogen. You add hydrogen in the presence of nickel or platinum, and then your double bonds become single bonds. So you're adding hydrogens to your carbon-carbon double bond. You add an H to each one, and now your unsaturation becomes saturated. All right, so that's hydrogenation. If you're doing hydrolysis means you're going to split something with water. All right, and so you can split your ester bonds and you can split it with water back into its carboxylic acid and its alcohol. All right, so that hydrolysis is splitting with water. Hydrogenation is adding hydrogen. All right, and so what we do to our oils that were nice and healthy is we do hydrogenation. Why? Because we like to cook with the solid, apparently. All right, so that's the only reason to go from something healthy to something less healthy. All right, so you're going to add hydrogen across the carbon-carbon double bond, and it's going to convert your double bonds into single bonds, and that's going to increase the melting point, putting it into the solid form. So your margarines are a reaction between your oils and hydrogen to make them saturated and make them solids. Unfortunately, in the process of hydrogenation, you do partial hydrogenation, and it converts some of your double bonds into a trans double bond because trans is more stable than cis. And so back in the day, when you bought your margarine, it had lots of trans fats in it, which were very unhealthy. They have since removed all the trans fats from just about anything I can find in the grocery store. All right, so you had your perfectly healthy oil, and you decided to you didn't like being cooking with a liquid. You like to plop in your lard or whatever. So you want it to be a solid, but you want it to be healthy. So you're going to use the vegetable oil and you make it into a vegetable shortening. All right, so you add your hydrogen with your nickel catalyst, and now you have converted all of your carbon-carbon double bonds into single bonds. Unfortunately, this is again if you see on your label, it'll say hydrogenated or partially hydrogenated. A lot of times they'll convert your nice healthy cis double bonds into trans double bonds, all right, which trans double bonds pack really tight, um, just like your saturated, because they have this. A trans double bond has the same shape, packs very tight. It's going to be a solid, except it's going to have the very unhealthy trans carbon-carbon double bond. All right, so again, you're going to take, oh, yeah, that was an interesting one too. So complete hydrogenation, you're going to convert your nice oil into a saturated fat. Olestra was a fat substitute, so it was supposed to be for fat-free eating, but when you have your fat-free stuff, it doesn't taste very good. But when it was made with Olestra, it tasted the same as your other foods. So you had your Lay's potato chips made with Olestra, and they tasted just as good as the full fat version of your Lay's potato chips, except they didn't have any fat in them. It was an artificial fat. All right, so this was great, except for the problem with the intestinal tract. So people would eat their chips while on the toilet. So didn't work out so well, and Olestra was kind of a flop. It was supposed to be the next big thing for losing weight, and well, it failed. All right, and they haven't really come up with anything since. That was a long time ago. All right, unsaturated fatty acids. All right, again, you want the cis carbon-carbon double bond. You do not want the trans carbon-carbon double bond. All right, so most of our naturally occurring fatty acids are cis double bonds. All right, so that's why our oils are going to be healthy. All right, but when you do a hydrogenation, when you're taking your double bonds and making them single bonds, some of your cis double bonds are converted to trans double bonds. All right, so trans fatty acids, they're going to behave like saturated fatty acids, except they are much less healthy than saturated fatty acids. All right, and so 2 to 4% calories in the form of trans fatty acids. All right, and so your trans fatty acids raise the LDL and they lower the HDL. They are not good for consumption. Avoid trans fatty acids, which is pretty easy. If you wanted trans fatty acids, it'd be harder to find, I think. All right, so you have more unsaturated fats in vegetable oils than you do for fats. That's true. Vegetable oils have higher melting points. No, they have lower melting points. They're liquids. Hydrogenation of oils converts some cis double bonds to trans double bonds. Unfortunately, yes, that is true. Animal fats have more saturated fats. Yes, so animal fats are saturated. Vegetable oils are unsaturated. All right, so again, that was hydrogenation, adding hydrogen. Hydrolysis is the other reaction. Again, that is splitting with water. And so you're going to split your esters, and you're going to use water, and you're going to get back what you lassoed. What did you lasso to form this? Well, you lassoed water. You lassoed water from your carboxylic acid and your alcohol. You lassoed water from your carboxylic acid and your alcohol. You lassoed water from your carboxylic acid and your alcohol. And so when you split it using water, that is what you get. All right, there should be a 3 in front of this. You got 3 molecules of your fatty acid. And to go back the other direction, you would have to lasso the water, and you would have to lasso the water, and you would have to lasso the water to go back to your fat. And so this is saturated, saturated, saturated. There's no carbon-carbon double bonds. This is a fat. It is a solid at room temperature. It came from an animal. All right, saponification. That is soap making. All right, and so we're going to make some soap. All right, so it is a reaction with a fat with a strong base. All right, so we're going to split, just like in the previous slide. We're going to take our fat here and we're going to split it. Now, when you do saponification, you do it in base. All right, so the catalyst for this example was acid. If you do hydrolysis in base of a fat, that is called saponification because we're going to make a soap. It is the salt of a fatty acid. So you simply take the H off of your fatty acid. So if you have your CH2 sub, let's go with 16 CH3 minus an Na plus, this is soap. So that is the salt, the deprotonated fatty acid. So a deprotonated fatty acid is a soap. If you use KOH and there is a K plus and then your O minus here, that would be a softer soap. Your sodium hydroxide will form a nice solid soap. It is lye soap because NaOH is called lye. It's kind of a hand soap and not a body soap. It is it's a very strong soap. It's good for getting oil off your skin. All right, so saturated. You've got a fat. You're going to add NaOH. All right, so 3 molecules of NaOH. We are going to do a hydrolysis, which means we're going to split our ester into the alcohol and the carboxylic acid that it came from, to the carboxylic acid and the alcohol it came from, alcohol and carboxylic acid that it came from, except now we are in base. This is a very strong base. We have a fatty acid, and that's going to do an acid-base reaction. And so you're not going to get the acid, you're going to get the deprotonated acid. All right, and when you have a long chain carboxylic acid, a fatty acid that has been deprotonated, you now have a soap. All right. So here is not hydrolysis. Hydrolysis is going to be splitting with water. This is hydrogenation. We're adding hydrogen. And you're going to add hydrogen to your carbon-carbon double bonds. And so this is a nice oil. And we are going to add hydrogen across not 1, not 2, but 3 carbon-carbon double bonds. And our oil is going to become a fat. Well, this is vegetable oil, and the product of this is called vegetable shortening. All right. Glycerophospholipids. All right, so this is where you have your polar head, and you've got your 2 non-polar tails. So these are the tails. This is the long chain of carbon. This is non-polar. This is hydrophobic. This is polar head. Non-polar, they call this the tail. And the polar head, and this, of course, is hydrophilic. All right, so you got your water-loving polar head. You've got your water-hating non-polar tail in your glycerophospholipid. All right, so the most abundant lipid in cell membranes. You got your glycerol, your 2 fatty acids, your phosphate, and your amino alcohol. All right, so you have an amine, an alcohol, so that's an amino alcohol. You've got an amine, you got an alcohol, you've got your amino alcohol. You've got your amine, you got your alcohol, you have an amino alcohol. And so a compound that has an alcohol group and an amine group, that is an amino alcohol. All right, so there are 3 main amino alcohols. You have to recognize that that's an amino alcohol. You do not have to know the structures of those. All right, so you got your polar head up here with your phosphate and your amino alcohol, and then you got your nonpolar tails. And again, they will draw it like this: your polar head and your nonpolar tail. All right, again, nonpolar tails, polar heads, yes, nonpolar tails, and polar head is there. You will not have to know the names of those, but you should recognize the polar head and the polar tail, nonpolar tail. Identify each. Okay, you got your uh, each has a fatty acid or an amino alcohol, or you don't need to know those, but you will need to know that they are made of a glycerol phospholipid. You got 2 fatty acids for the 2 tails, and the polar head has a phosphate and amino alcohol. All right, steroids. Easy to detect a steroid because it is a ring system where you have your 3 6-membered rings and your 1 5-membered ring. So if you have 3 6-membered rings and 1 5-membered ring, then you are a steroid. That is all you need to know about your steroids. You need to be able to recognize your steroid nucleus and know that that is a lipid. All right, so cholesterol, since it has this ring system, cholesterol is a steroid. All right. All right, so again, in C, this tells you that you have the steroid nucleus. All right, so of course you will know a hydroxyl group, that is simply your alcohol. You know a methyl group is CH3, and you know a carbon chain is a bunch of carbons in a chain, so that's D. All right, so the thing that you need to know about this one is you have a 6-membered ring, a 6-membered ring, a 6-membered ring, and a 5-membered ring, and that is your steroid nucleus. No, no, no. Your steroid hormones, you don't need to, whatever. All you need to know about your steroid hormones is that they all have this same ring system. That is what you should notice about all of your steroid hormones. They all have that steroid nucleus. Whether they are legal or illegal, they have the steroid nucleus. All of these have the steroid nucleus in them. So you should recognize that as a steroid. If it says what kind of compound is that, and steroid is the answer. You will not have to know the names of the specific steroid, but you have to know that these are steroids. You have to know this. Steroid, steroid, steroid. You're just looking at the ring system and you know it is a steroid. All right, then you got your phospholipid cell membrane. Okay. You got your phospholipid bilayer. So note that they are just showing your cartoon. You got your polar head. So this is polar. You got your non-polar tail. So everything in here, you got your tails, your tails. It's a bilayer because you have your tails going up. You got your tails going down in this 2-layer system. So you got non-polar in the middle, and then above is polar, below is polar. All right, so they're pointing to it there. So the non-polar is where the tails are, the polar is where the heads are, and this is a phospholipid bilayer. We're not going to do that or that or that. That's just your phospholipid bilayer, and those tails are long chains of carbons. Let's go to 16. All right, so a little review of our amino acids, proteins, enzymes. All right, we went through this yesterday. All right, so your amino acids, all of the naturally occurring amino acids are L amino acids. They're alpha amino acids. We already went through that. Okay. Glycine is the only one that is not L, because glycine is the only one where your carbon is not chiral, because now your carbon is connected to two hydrogens. But if you put your methyl group on there, now you've got a chiral carbon and you have L-alanine. All right, you have to know the non-polar side chains. You have to know the polar side chains. And any side chains that have a carboxylic acid, that is going to be the acidic side chains. All right, and then the basic ones are going to be with the amines as the side chain. All right, so you've got your basic, you've got your lysine that has the amine, and then of course you have your carboxylic acid side chain with your aspartic acid, that is an acidic side chain. All right, so here are all of the nonpolars. Again, these are the ones that only contain carbon and hydrogen. The exception is methionine, which has a sulfur between two carbons, and your tryptophan, which is also nonpolar, even though it contains a nitrogen. And then the polar ones, they all contain an O. The ones that don't contain an O but are still polar are your cysteine. And on the next page, you have your two acids. Of course, you're acid or base, you're polar. And so all of these are polar. All right, so here is your carboxylic acid group, aspartic acid. Here's another acid group, glutamic acid. All right, so these are acidic amino acids. So there are two acidic amino acids, and you would know that by their name, calling them acids. All right, and also by structure, you have a carboxylic acid group. There are three basic amino acids, histidine, lysine, and arginine. Those are the three basic amino acids. All right, so this one has two nitrogens. Your lysine has the one nitrogen, and your arginine has three nitrogens. And so these are nitrogen bases. All right, so these are all polar. If you're an acid or a base, you're polar. All right, so you have two acidic amino acids and you have three basic amino acids. And at the bottom, it gives the pKa's, or it gives the pH of these. So you have a high pH, it's basic. You have a low pH, it's acidic. And if we go back and look at the pHs of the nonpolars, all right, so they're in the 5 to 6 range. Yeah, 5 to 6.3 looks like are the lowest and the highest. All right, so then, so if you are then above 7, so 7.6, 9.7, 10.8, now you're a basic amino acid. And if you're below the 5, this is a 2.8, that's a 3.2, then you're an acidic amino acid. All right, so polar, nonpolar, if it has an H, it is of course nonpolar. It has an O, it is polar. So you're looking at the side chain. If you only have carbons and hydrogens, it's nonpolar. If you have an oxygen on your side chain, it is polar. All right. So again, all the naturally occurring amino acids are L amino acids, but if you take the mirror image, you can go from L-alanine into a D-alanine where your NH2 is on the right. D-alanine is not naturally occurring. The L amino acids are used in protein synthesis, and they are the naturally occurring amino acids. All right, so again, if your NH2 is on the left, it is L. If your NH2 is on the right, it is D. The naturally occurring amino acids are the L amino acids. If it states to write your amino acid in a zwitterion form, all right, so here would be glycine, and if it says give glycine in the zwitterion form, you know that your acid is the proton donor and your base is the proton acceptor. And so what's happening is this base is taking this proton, and so now you have NH3 that has a plus charge, and now you have O minus here. And so a zwitterion is a dipolar ion. The nitrogen will have a plus charge. Your oxygen will have a minus charge. All right, and so those pHs that were given, those are the isoelectric point. So that's when your charge is 0. So it is a neutral glycine at that isoelectric point. All right, so if we have our glycine and we stick our glycine in base, so we're going to do an acid-base reaction. And so your OH is going to take the H off. And so now you're going to have a negative charge. All right, and so this would give you a -1 charge. The next slide is going to be putting it in H+. If you put it in acid, now you're going to put that H back on your carboxylic acid, and you're going to have a plus charge. So again, you have H+, you're going to put the H back on, and now you have a plus charge. So in base, you have a negative charge. In acid, you have a positive charge. If it is at its isoelectric point, then it is a charge of 0. So here is at the isoelectric point. You throw in acid, and now it's going to be plus. You throw in base, it would be minus. All right, so here they show it all in one slide. So here you have your neutral amino acid. You throw it in base, and that's going to become minus. You throw it in acid, it's going to become positive. All right, so alanine above its isoelectric point. So pH above, that means a high pH. That means base. That means negative. pH below, that means low. pH, that means acid. That means plus, H+. All right, so this one is in acid, and this one is in base. All right, so you should know that base, high pH is base, that means negative charge. Low pH is acid, that means plus charge. Base is OH minus charge. Acid is H plus charge. All right, so your peptides, again, you're going to take your, I like to not use the zwitterion form for this. I prefer it to be in its neutral form. Either way is fine. But when I lasso water, I want to lasso water. All right, and so I'm going to lasso water here, and then I'm going to form my peptide bond. So this bond is a peptide bond, also called an amide bond, because you are forming an amide group. So this is your amide group. All right. So again, we're going to lasso water. They have all 3 H's here, so fine. We're going to take 2 of these, not all 3. We're going to take H2O, and we're going to leave 1 behind. So then we're going to form our amide. Now note when we're writing these, we want our nitrogen on the left and we want our carboxylic acid on the right. Always when you write your peptide, the nitrogen group on the left, your carboxylic acid group on the right. All right, so again, if you bring together two amino acids, you have a dipeptide, and a dipeptide has one peptide bond. So the dipeptide means you use two amino acids, but when you combine two amino acids, you only created one peptide bond. All right, so name the tripeptides. So you could have glycine, glycine, alanine. You could have alanine, glycine, glycine, and you could have glycine, alanine, glycine. So that would be the three ways that you could do your tripeptide. So glycine, glycine, alanine, glycine, or alanine, glycine, glycine. So there's three ways to put your three amino acids as a tripeptide. Note, it's a tripeptide because there are three amino acids, but these are your peptide bonds. A tripeptide has two peptide bonds. If you got one of each, you got LGA, you've got LAG, you've got GLA, you've got GAL, and you've got AGL, and you got ALG. And so you have 2, 4, 6 possible tripeptides if you have one of each of these amino acids. So start with L twice, this way switch them, A twice, this way switch them, G twice, this way switch them. Is how you get your 6 possible tripeptides. And again, tripeptide has 2 peptide bonds. All right, so you won't have to label the 3 letter abbreviation, but you should note that you have the side chains, the side chain, the side chain, and the side chain. All right, and so here is a non-polar side chain. Here is an error because I'm not sure what they want here. I'm hoping they want an CH2 there. And that's a non-polar side chain. This is cysteine. This is one that doesn't have O but is polar. This is methionine. This has also sulfur, but this sulfur is between 2 carbons, and this one is non-polar. So the question you're going to get from this on the test is the side chains, polar or non-polar. And so non-polar, non-polar, polar, and non-polar. All right, so then when you do your proteins, that is going to be giving your primary structure, which is your sequence of amino acids. So we had 2 questions before. We had 2 amino acids, and they were 2 different ones, 2 of one and 1 of the other. There were 3 different primary structures. If all 3 were different, we had 6 different possible primary structures. So the primary structure is your sequence of amino acids. All right, so that is the primary structure. All right, primary structure. Secondary structure, we went through this a little bit. That is the hydrogen bonding that can lead to a alpha helix or a beta pleated sheet. All right, so that is a secondary structure. So alpha helix, beta pleated sheet. You can also get a triple helix as your secondary structure. All right, so when you are hydrogen bonds, when you have your hydrogen bonding, that is a chains held together side by side, hydrogen bonding. So you got your beta pleated sheet, you got your sequence of amino acids. That is your primary structure. You got your corkscrew shape. That is your alpha helix. And then you have 3 peptide chains woven together. That's your triple helix. And that one. All right, you have essential amino acids. I'm not going to have you memorize those, but what are essential amino acids? These are the ones that must be obtained from your diet. All right, so you have to, if you are a vegetarian, make sure you are not eating the same vegetables, because if you're not a vegetarian and you have meat and dairy products, they are complete. So they have all the essential amino acids, but when you have your grains and your vegetables, they are missing one or more of your essential amino acids. So you wouldn't eat the same grain every time. All right. I'm not going to get through all that. All right. We will pick up there next time.